One of our members is about to install a three-way point on his layout, operated by servos but controlled by push buttons, and he wanted to know what was the best way to implement that. So why do we use three-way points? Well, it may be because it fits the prototype of the layout you're building, or commonly as a means of saving space on the layout. If we want to have 3 output tracks, normally we would use 2 points, as you see here. Whereas if we use a 3-way point, we've got much more track space available. Now, there are already out there on the internet various schematics about how to control 3-way points using solenoids or tortoise motors, as you can see as examples here. There's tortoises, there's solenoids. In fact, there's one in the top left using push buttons to control solenoids via various routing diodes. But we want to look at operating with servos. So the specification for this project is that it's going to be servo operated, controlled by push buttons. That will be LEDs on the control panel which indicate which options have been selected. So if you press to go into the center track, then the center LED will illuminate, for example. So it always lets you know what the current settings of your point are. And finally, that is able to control relays for frog switching. So, moving on, there's the Pico 3-way point. Let's look at descriptions we'll use when working out an approach. Well, the member wants to call them left, centre and right as the 3 output tracks. He wants to call the inner tie bar 1 and the outer tie bar 2. And he wants to call the positions A and B. So when the tie bar is moved vertically, as in that diagram, it's moved to position A. When the tie bar is pulled downwards, it's moved to position B. So there are 2 tie bars and 4 possible positions. In addition, we have 3 frogs on the point. Here's what we're working with. 3 push buttons, 2 servos that control 4 different tie bar positions, polarity of 3 frogs, and the illumination of 3 LEDs. To make all that work with push buttons, we have to look at some kind of microcontroller, either a PIC or Arduino. So I've chosen in this example to use a PIC. Let's look first of all at the mechanical movement of the switch blades, in other words the tie bar settings. Here is a close-up of the point minus the switch blades. So let's look at the switchblade positions that were required for the 3 output tracks. If we're going to the center track, then as you can see, I've got arrows that point to the active blades. So this one is going to touch here, that one's going to touch there, and the yellow rails play no part in the routing of the loco. To move the tie bars in that direction, as you can see, we've had to move tie bar 1 to the B position, tie bar 2 to the A position. So we can say that the centre root is 1B and 2A. Put that into a table for the tie bar positions, like that. And then we can do the same for the left position. And once again, I've put arrows to point to the active point blades. And once again, the two that are marked in yellow play no part in the routing. To make that work, we've had to move both tie bars up to the A position. In other words, left equals 1A and 2A. Place that into our little chart and then do the same for the right. In this case, I haven't put a blade here because it plays no part in the routing. Once you've set this particular blade, the other one has got no effect. So we'll have to move one blade to achieve the right output. So the right output moves blade 2 to position B, and tie bar 1 plays no part, so it doesn't matter whether it's to A or B. Put that into our chart, and there's our tie bar positions. We can now use the same mapping technique for frog switching. What frogs do we have to switch to what polarity for each of the output tracks? The same as before, we'll add in the fact we've got 3 frogs, we'll call them 1, 2 and 3. And for polarity, you'll see on the right hand side, we'll call them red and blue just for clarity. So, what do we need? Well, if we're going to the left, we have to have frog 1, 2 and 3 all set to red to continue that all the way through. So left is red, red, red. Let's make another little chart for that. All frogs are the red polarity for going left. If I go into the centre position straight ahead, it's a little bit different. Frog 1 now has got to be set to the blue position, whereas frog 2 and 3 have to be set to the red position. Add that to our chart, and finally to the right, once again, it doesn't matter what polarity this frog is because it plays no part in the routing whatsoever. The local won't be going over that frog. And we have to set frogs 2 and 3 to blue to continue the polarity all the way through. And we feed that into our chart. So there's the final chart. But you might notice something, that frog 2 and frog 3 polarities are identical for each of the 3 positions. So we don't need to have 3 outputs, we can simply connect frog 2 and frog 3 together electrically and switch them both at the same time. And that will simplify later on. If we then amalgamate the 2 tables, we can see this. If we want to move to the left position, there's the 2 tie bar positions, there's the 2 polarities that we need. Whereas the centre is different tie bar positions, different frogs. And the right, again, different settings. This is going to help us later on when we have to program the chip. For example, we now know that if the left button is pressed, we have to move servo 1 to A, servo 2 to A, and make the 3 frogs all be red. So we know the logic now. We haven't written a line of program yet, but we know where we're heading. Hardware wise, we need a microprocessor that has got 3 inputs for the 3 buttons and 3 sets of outputs, 2 to control servos, 2 to control relays, and 3 for the 3 LEDs. The 2 at the top here can connect directly to servo modules such as Easy Points or the Servo 4 board, or can be used as inputs to the Easy Bus or C-Bus modules. The relay outputs would connect to relay modules for frog switching, and that's what I've chosen to do with the pick. There's the 3 input buttons down the left hand side, there's the 2 relay outputs, the 3 LED outputs, the 2 servo outputs. In terms of the program, that's the comments I always include at the beginning of a pick program to remind myself what goes where hardware wise. It's worth saying that in this, all I/O pins will be active low. That means they're normally held at 5 volts, and to make something happen you bring it down to 0 volts. So when you press the push button, the inputs on that pick will drop from 5 volts down to 0 volts. And all outputs will go low when they're activated. So a low output will switch a LED on. A low output will switch the relays on, and the tie bar outputs will go low to switch to position A. That's design choices for the program. The member also wants the left output track to be the default. So it makes sense that the relays are switched off when they're in the default position to save current. That we only switch the relays on when we're going to the other output tracks. So here we have the original table, and we can change that and translate it to what's going to happen in terms of the outputs. So we know, for example, that when in the default left output track, we want the relays to be off. So that's going to equate to high and high. And we'll want the servos to be low and low. So now we have the top talks about what we want to achieve, and the bottom table describes how we're going to achieve it in terms of the coding. Yes, they say the proof of the pudding is in the eating. How do I know that this project will work? Well, I don't have a 3-way point to test it on, so I'll have to make up a bit of board with LEDs that represent the relays and represent the servos, etc. And then make up a board that will contain the microchip pick and connect it all to the buttons and all the other ancillary pieces. And then finally get round to the coding. So I can do all of what we've discussed so far and what I'm going to show you next without even getting to the point of writing a single line of code. Right, let's start with the hardware first. Now, since I don't have an actual three-way point to work on, I've made up a quick board just to test it. So here are the push buttons, here are the track indicator LEDs. These represent the frog switching relays, and these represent the tie bar servos. And this is the hardware we came up with. A piece of Vera board with a 14-pin chip, the PIC 16F676. You can see the voltage regulator here. The black and the red are the 12 volts coming in to supply the module. The orange wire is 5 volts going out for LEDs or other ancillary uses. The two connections here are going out to the relays to operate the frog switching. The three connections here are coming in from push buttons to those pins that are currently held high with these resistors, and pressing the button brings those 3 pins low. Those two outputs here go to the servos to operate the tie bars. And this set of 3 outputs here are for the LEDs, and the outputs already have 1K droppers on them. And here we have the strip board now mounted on the little test board, all ready to go, with a 12 volt supply coming in from the left and all the outputs connected under the card to the various LEDs and buttons. So what do we need to do now? Well, we need to start looking at what code's going to go inside that chip. The code for it is written in JAL and then compiled and programmed with a PIC kit. We're going to test for all 3 push buttons one after the other, like so. So to meet the top condition of the table, if the left button is low, that means it's been pressed. And if that happens, we know we want to make that go low, that go low. We want to make sure the 2 other LEDs are switched off, but the left LED is switched on, so it's going to go low. And we want to switch off both relays because that's the default position. Simple as that. And we do something very similar if it's the right button or the center button. All we change is whether they go high or low, according to that table. The only change is I've added another piece of code in here to help prevent false triggering for like commutation or any interference. What we're saying is, let's set a variable to say that valid equals true, and then 40 times we go round the loop. Now the left button starts off as low, and it should end up with valid true at the end of this loop. So 40 times we're checking. And if at any point during those 40 tests we test a high, in other words interference, then valid becomes false. And after checking 40 times, we come out the loop. Has it stayed true? Have there been no highs during that 200 milliseconds. No, good. Then there's no interference. It's a genuine push too low, in which case we carry on doing the tasks. Right then, let's have a look at the final code written in JAL. At the top, a set of comments explaining what the program's about, who wrote it and when. And then, as we saw a moment ago, we have the pin layouts to remind us. And then all the usual setups that you get, picking the frequency, all that kind of stuff. And then deciding which pins will be outputs, which pins will be inputs, and declaring them that way, with comments to remind me as I go along. And then setting up the actual variables themselves for the buttons, the servos, the LEDs and relays. And at the bottom, the main program, when you first power on, we said we wanted to default to a left output track, which means setting the servos that way, bringing on the left LED, putting off all the other LEDs, make sure the relays are off, and it'll stay in that position until you press a button. So we've got a loop now that's going to go and check all three buttons. And to keep it simple, they're all identical except they do slightly different things. So to check for the center button, the code we saw earlier, check if the button is pressed. If the center button is pressed, make sure it's a valid press rather than some interference. If it's valid, then set the servos and LEDs and relays accordingly. If you haven't pressed that button, you ignore all that and you jump down to the next test. Well, in that case, is that button pressed? And if it is, you do that, and if it isn't, you go back and do that. And when you finish checking all three, if no buttons are pressed, you go back to the beginning and it says go and do it all again. So keep on looping between those three tests until you do press a button, and then it'll change the hardware accordingly. Right, here we go. This is the test setup. What happens when we first apply the power? Well, it's routed to the left. It's energized both of the servos to go to position A, which is what we want to make it come around here. If I now press the center, now we have one servo not activated. It's going to B, and that one's going to A. And we've got the frog, one activated, and the LED routed to the center. And if you press right, once again the indicator tells you it's moved to the right. Both of these are not active, so they're both going to go to B, which is what we want to make it go this way, and it's brought on the appropriate frogs.